discussion with regard to indexing and using different ways of how we can build an index. So what do you see here in this? Oops. Yes. So what do we see here in this plot is a schematic way to indicate time complexity analysis. So when algorithms are developed, there are specific ways to express the complexity, the time complexity specifically. So if I'm going to write for loop, which means I need to visit a set of elements. So for I, which would belong to some range, maybe starting from 1 to up a value of n, okay? And then I'll be doing some operation, okay? Maybe, you know, update some value. So A is going to equal A plus 1. And that's it. So this is one loop. So I have, we indicate loops usually by n iterations. If I end up having another nested loop, okay, and we use another index j, nested loop mean I'm going to have a for loop inside the outer one. And this is could go, you know, we could start from 0 to n again, okay, and maybe I'm updating another number, okay, that depends on a, and so on and so forth. So for each iteration then, for each iteration, I'm running n times, which end up that for two nested loops, n by times n, this is going to equal n squared. In a nutshell, when we look into algorithms, we keep our eyes on these loops because they can be intense. Having a loop, sorry, this is not n to the power, not n to the power n, it's n to the power 2. And so we use some terms to refer to this complexity. Now, in algorithms, complexity analysis and computer science, sometimes we trace actually the actual step counts and get the constant numbers. Like, you know, this is going to be n minus k plus 1. There is an extra step. But we don't actually care so much about constant values, okay? Sometimes these values. So there is a notation to use, which is referred to as big O complexity. So instead of saying, this is actually telling us, well, this is the dominant term, so use big O notation to say that this is the number of steps. Anyway, without diving into this so much, of course, if you're interested, we can discuss this more during the office hour, or, you know, drop me a chat message to learn more about this. But let's go back here and see if this is a linear line n, means we need to execute for n steps, right? We have done n, we looked into the full data structure before here. We used the schema index, right? The schema array. And if we need to go and check everyone to know the locations, then we'll do n comparison. However, if we use what's called the binary search, which is nothing except look at the middle value, since this is lexicographically ordered or alphabetically ordered, or, you know, numerically ordered, whatever is the ordering technique, look into the middle value, and then, you know, if it is larger or smaller, you dive into the other part. And so we end up, since it's a binary factor, and we are going by either left or right, we end up into what's called a binary tree. And usually the number of steps there is going to be indicated by log base 2 n. So instead of executing n steps, we'll end up with log n. When you see the log curve, which shows you how much is this efficient. So if you get nothing about complexity analysis, except that, you know what, we can do a wonderful job by using this binary search algorithm, is good, because we move from that number of executions to log n of executions. So even the worst case scenario, we know it's only going to involve about roughly 20 steps of operations for searching for a k-mer. Yet, although k-mer indexes that we looked at are good, we need to do better. We still need to do better, okay? Because we are doing log n, think about n as the size of the full number of comparisons. And you may think about the size of the genome. Okay, so think about all of these numbers that would relate to n. These are big numbers. Even if we take log, we may end up doing thousands of operations. We have millions of seeds and seeds by the end of the day that we are extracting from the reference genome. So what if we can jump from big O of this value to big O of 1? That is a constant. So do it in one operation. That would sound a crazy proposition for the moment, okay? But you may give it a chance and see the beauty of computer science. Now, before diving more into this, you need to know that the memory on your machine, that there is a memory chip called random access memory. For example, there is the constant memory. Sorry, that is, for example, the hard disks and hard drives and these devices like USBs, you actually store the data there, so it doesn't go away once you shut down your machine. But random access memory is different. It's there to help us processing the algorithm. It actually comes in a shape similar to a table, and each one has an address. You can think of the memory, the actual memory chip in the CPU or in the computer in front of you. You can think of it as the mail service center that you go to, and you find many mailboxes with lockers, okay, and keys that you can use. Each one is a place to store some information. However, this layout of this hardware, piece of hardware, needs some management. And so to arrange this in certain interesting way, like to have the access, because we have different types of data when it comes to computers. We have integers, floats, strings, characters, and so on and so forth. So we need some software to take care of this. So usually the operating system and the programming language that we are using is helping us to figure out how we arrange the blocks of this memory into some interesting data structures. For example, think about arrays, which is nothing but contiguous allocation of memory blocks. Or think about what's called a linked list, which is kind of a list implementation where it doesn't need to be a contiguous memory allocation. So I could have one memory allocated for this position, and here this is the other one for to store a second value, and this to store third value. They don't need to be next to each other, contrary to the array, which needs all the elements to be next to each other. And so this area of how we can develop these different implementations to arrange our actual memory architecture and our actual memory tables. This is what we refer to as data structures. The data structures is this key concept in computer science, which refers to again, allocations of memory as storage units and operations that we can apply. We need operations to access this data. So we need to define how we can access the second element here, and how we can add one more element here, and so on and so forth. Not only this, these are primitive types or primitive data structures that can be used to build more data structures, like trees. So we can model this as something to have a left branch and right branch, and so on and so forth, or queues, or queues, or stacks, and so on and so forth. Many data structures. So going back here, let's dive in. And one thing we are going to do here is we're going to visit mathematics and look to what's called the hash. There is what's called the hashing function. Now, this is a function that is given for us with certain guarantees, which is interesting, okay? You give it an input, it's going to then directly give us the value of where we should go. So now, instead of breaking this table and comparing to the middle, and then jumping to the middle part if it is greater than or less than, and so on and so forth, instead of doing all of this, directly shoot to the right position. Now, for a moment, this would seem like, how would that be even possible? Everything we discussed before seemed reasonable. How can we use just a function and we end up with this, okay? And again, this is the beauty of what's called the hash function. It's once it's calculated, it's going to give us the address for a location in this hash table. So let's look into this and see how we can do it. Okay. So there is some hashing function, okay, that it's that we can use to do some operations, okay, and then using this hash function, we can actually, we can get into the location, okay, and we can come up with different hash functions. So in this case, there is an input that will take us to position 7, so we know it's directly here. Okay, this is the input. So let's now go and revisit our previous example. So if we want to create a hash table, okay, sorry. Okay, sorry for that. Yes, I hope you see everything well. So let's keep going with this discussion. So if you want to create a hash table based on k-mers of length 3, so patterns taken from the original genome of length 3, we would know that we have 3 slots. Each one can take ACGT. So this is 4 options, 4 options, 4 options. So 4 times 4 times 4, this is going to equal 64, 4 to the power of 3, which equals 64 possible arrangements of ACG, GCC, TTT. So keep going, you get 64 variations. So we need a hash table with that size. And then we can take part of our example here and say, for example, there is a hashing function that's going to take this GTG and then store it at position 6. So if we do this, which means the hash function is going to take this input and then store it here and give us the access information that GTG is here. Okay, and then TGC gave us 63, so we store it here. Okay, and we keep going until we finish going through everything and we build our hash table until we go through the whole genome. Okay, now we need to append to this some information. We need to store the positions of those. So when we say there's GGG, okay, where did we account GGG? Well, at position 9, 10, and 11. So we need to store this information as well. Okay, so as we build this table, going back to this, we are actually adding an extra information, that is the location, because this is important information for us that we need to use. So now, given our example, imagine we have the same read as before, and so we will use TGG in this case, and it returns 3. So we know that at position 8 of the sequence, so we count here 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is location 8 here. So this is GG. Oh, sorry. This is okay. Okay, this started 0, 1, 2, 3, 4, 5, 6, 7. Okay, so maybe in this case, this was counted, started by 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, there is 8 in this case. It's here. And so we have TGG. Okay, TGG. So we know the numbers. So given a TGG read, then we can expand this for verification purposes and see if it works, and we find our sequence. Okay, so now we even save more time than log n base 2, because we are doing this in one single step, step. Okay, now let me show you like quickly some example, like um, let's do this. Okay, choosing a hash function here. Okay, so let's use just a rudimentary hash function that converts each nucleotide to a binary value. Assume this is our hash function, which says A, the binary value of A is 0, 0. Just assume this is sufficient, and it works, okay? And 0, 1 for T, and then for C, it's going to be 10, and then for G, this is going to be 1, 1, okay? So this is our hashing function. So now we want to convert G to GTC. Okay, and convert to C using the above mapping. And so in this case, we know that G will have 1, 1, okay? And so let me change the color here. So using this mapping, using this hashing function up here, so we have 1, 1 for G, good, and then we have 0, 1 for T, nice, and then we have what? 1, 0 for C. 1, 0 for C. Combine them, we get this hash value. So now you can consider that we have used some hash function. That is our hash function. Again, it's rudimentary hash function. Okay, and then we get this output here. Now, this value that we have here, we can convert it into decimal value. So usually the way to do this, okay, to convert binary to decimal is by saying, you know what, this is 2 to the power of 0 times 0 plus 2 to the power of 1 times 1 plus 2 to the power of 2 times 1 2 to the power of 3 times 0 plus 2 to the power of 4 times 1 plus 2 to the power of 5 times 1. And so we add all these numbers. This is how we do the conversion from binary to decimal, so we get 54. So eventually we got this value here, and we put hash, let's say this is our hash function, and GTC gives us, using this hashing function, 54. Okay, of course there are more advanced hashing function that would achieve the goal, but then we can go and given an array data structure in Python, for example, or some programming languages, we know that now array 54, position 54 is where we have GTC information. And so there we can put or append the information of indices as we go. So maybe we find 1 at 0, and when we hash again GTC sequence, because it appears again in the genome, we put position 121 because that's the position, and you keep going, okay? However, we use three-mers here, okay? This is not practical for the human genome. Three-mers does not contain enough information. For example, we know from the DNA replication, an interesting pattern would be of, which is the DNA A box there, is of length 9. Okay, the hidden message there telling the DNA A protein to unfold the DNA is of length 9. So another treasure hunt question for you is, can you think of another pattern which is higher, could be higher than three-mers or k-mers, and tell me what would be that in the human genome of interest. Okay, we have many examples that we discussed before. So now how would this change things? Well, instead now of 4 times 4 times 4, we end up with 4 million, more than 4 million possible slots. So we end up with the big table And that is not very efficient because now we are using memory and we start to see it, right? If I want efficient data structure that use memory and I keep using the memory, so we get into this competition in computer science always between CPU and memory. That's why usually, even if you go to the cloud resources, they ask you, do you want more CPU? Do you want more memory? Or both, of course, depending on the application. But usually, sometimes the application are more CPU intense. Sometimes they are more memory intense. In this case, this is huge. So we need to save something. So we go into a strategy, which is let's shrink the table, okay? We don't need a perfect hash table, which means we have to make sure for every pattern there is one slot. No. So what we do is we can go ahead and use just a limited hash table of size 27, for example. Okay, and then we give, in this case, similar to example that I've shown you with binary values, let's give A value 10, C value 20, G value 30, and then T value 40, okay? And so let's hash this. What's gonna be the hash for this? It is, we have how many A's? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 10, we have 90 here, plus we have 2 T's, that's 80. So we're going to end up with 170. So this is exactly this. Based on this hash values assigned for the nucleotide. Now we take 170 and then we modulus mathematical operation, which is going to give us the remainder. So 170 modulus 28, we get 2. So hash it to here. So this is now, once we introduce the modulus, it means go in a circular fashion. So you don't need to have a big one. But what is the catch here? Another treasure hunt question. If we do this and we keep doing this, what is going to be the issue? Now we survive from that issue of having a very long table. True, good. But now we have a very small table. Can you tell what's going to be the issue? And again, for all of my questions, especially if it comes to parts where they are new for you, feel free just to say, I don't know, I didn't get it. But again, try to think, what could be the issue now? What's going to happen? Okay. Well, the issue is, let's keep going. I have another sequence, 440, I get to position 20. Now, you see this? I have this sequence, which is different than this sequence. So this is what's going to cause what's called a collision. Collision is kind of, accident, car accident. I have now two sequences going to same area. So what do we do? Do we surrender, or do we regret this idea, or what? No, of course, you add extra steps. So this is what you do here. When this collision occurs, we append it to the a hash table, and through what's called the linked list. And then eventually we keep going, okay? And so this is what we end up with as a lookup table. Of course, it's going to increase some steps. So it's now, from now on, whenever something is to map to here, we need still to check which one it is, right? So we end up with more slots. So some of the earliest read mapping tools developed for large volumes of large used hashing, okay? So hashing is always there as an efficient data structure, yet typical hash tables would still require roughly about 40 gigabytes. This is a big issue. Believe me, when it comes to genome alignment, it is a challenge for computer science, and I'm a computer scientist by practice. It is that field that causes challenges in terms of memory, computation, alignment, algorithms, everything. And this makes it interesting for me personally. So it is big data. We are dealing with memory issues, algorithms. So throughout the years, of course, there have been good progress with those tools. And there are many other ways to index this data other than just the hash table or arrays with binary search and so on and so forth. So let's look into what's called suffix tries, okay, which are a very interesting data structure. And I hope you will enjoy it. It's this kind of a tree data structure, a simplified version of what's called some suffix trees, or a different version of what's called suffix trees. And these all relates to one family of indices. So let's look into this, okay? This is our example sequence. And again, imagine that this is the DNA sequence. One thing we need to do before we jump into building the index here is adding a $ as a terminal or terminating character, okay? This is the convention here to add this here, and see how it's going to help us, okay? And we assume it has it's the first letter in the or character in the alphabet, and which meaning having a less value than those. So giving the sequence, the first thing that we need to do is define what's called suffix array. Okay, so let me try to draw CATA. Okay, and then another TA. And suffix array is nothing except writing everything down with $ and then drop the first one and say start with A and end up with the terminus and keep going. Okay, we are doing this until we get here. So often this is omitted, we don't need it. So this is what's called suffix array. This is how we start building our suffix try, and try is this word comes from retrieval, okay, from retrieval, and we pronounce it as try, okay? So let's see the suffix try, how we can build it. Well, when we see when we are saying tree or try, these concepts or these family of data structures, we have some nodes and edges linking things to each other. So we take the first sequence, and starting from the first position here, we have C. We put it here in this position. Okay. So we have here C, A, the edge, T, A, T, A, and then a $. So we have taken all of those. Now, what do we do next? So this is our first path in that try. Next, we move to the second one, and this is an A. Well, A does not start with C, so we're going to establish another path to it. So it's A, and then we have, we put this, we have T, and we have, what's next? We have A, and then we have T, and then, well, this is A, T, and then we have an A, and then we have our $. So we have constructed this one. And then keep going with the same thing, T. This is another path here. So this starts with T, A here. So this is TA, and then a $. Good. Let me change the color here. And then we have ATA. Well, I already have A. So A is here, and T is here in this path, and then A is here, okay? So I already have this path defined here, okay? But I will do some change. So let me show you. This is the first one. This is the second one. And now I'm moving to this. So since I already have that path, the change that I will do, I will add an extra edge defining that there's a terminus, which is adding this character. And what about TA? Well, this is TA. Add another $ here indicating the terminus. And that's it. So keep going by developing this data structure. Now, finally, we replace these $ with what? With the positions. So we know that this is 0. This was the first one. Okay, this is the position of the first substring. And then we have 1 here, and you keep going. So we replace those. So it's going to be 0, 1, 2, 3, 4, 5. Okay, let's see how we can use it. Okay, so now imagine we have a substring, okay, that we are querying here. Okay, so what about searching for the sequence TA? Well, this is path T and this is path A, okay? and we have a terminus here. So we know at location 4, there, or position 4, there is going to be TA. Not only this, go to the bottom, because everything else is also having this as a substring. Okay, because everything else is going to have this as substring. So at position 2 as well, we get this number 2 telling us that everything, because we go, this is one path, so it means TA is part of this and TA is part of this. So position 2 and position 4, and here you go, you get your sequence using this data architecture structure. Okay, so matching a string using the suffix trie is fast. Okay, and it's in fact proportional to the size of the query, not the reference. However, it uses also a lot of memory and takes the memory footprint from n to n squared, so it makes it huge. If we're looking to a genome size, this is prohibitive. Okay, so more other types of data structures are used, like suffix tree, which is a modification of the suffix trie. So these are groups of data structures that one can use in different implementations that will be already used actually to help with the implementations. The final part is we're going to discuss alignment, and they will be exercised after we have dived into, the indexes and RNA-seq alignment and so on and so forth.